We continue the chapter 13.3 with the probability of the intersection and with probability trees. So the probability of the intersection can be found as a product, probability of E times the probability of F given E. Let us see it on the example with a drawing of colored balls from an urn. We have an urn with a total of 15 balls, 3 red, 5 blue, 7 green, and we want to know the probability of getting red, and blue balls in this order. So we continue three stages of this event. So first, we draw the red ball. Probability of getting first red ball will be the fraction in the numerator, the number of red balls, there are 3 here, divided by the total number of balls. So the probability to get a red ball is 3 to 15, 3 over 15. We can simplify this fraction dividing by 3 numerator and denominator, 1 over 5. Then the second stage, we want to draw a second ball, which is also red. Probability of getting second red, given that the first was red. So then, now we have only 14 balls, so one red is already not there. Now we should draw from 2 red, 1 from 2 red balls from the total of 14. 2 over 14 is the probability to get the second red, given that the first was also red. We can simplify this fraction as well by dividing by 2 numerator and denominator, 1 over 7. Then the third stage, we draw the third blue. What is the probability to get third ball blue, given that the first was red and the second was red? So we have 5 blue balls, and the total number of balls in the urn is now 2 reds and gone. So 15 minus 2, 13. 5 over 13 is the probability of getting third blue ball. These are probabilities of getting one ball from the given number of balls. And we want to know the probability of getting red, blue. The probability of getting the first red, then multiplied by the probability of getting the second red, given that the first was red, times the probability of getting the third blue, given that the first was red and the second was red. When we multiply all these probabilities, you will get actually the probability of the intersection, or the probability of first red, second red, third blue. So the probability that we actually want to find. So, and this is equal to the product 1 over 5 times 1 over 7 times 5 over 13. We can simplify it a little bit. We have 5 in the numerator and 5 in the denominator. We can cancel them out and we get 1 over 7 times 13, or 1 over 91. So we can also find the probability of getting green, red, blue in this order. probability of getting green times probability of getting the second red, given that the first was green, multiplied by the probability of getting the third ball blue, given that first was red and the second was green. Probability of the first green. We have 15 balls. We can remove these marks. Now we have, again, we have 15 balls. So the probability of first green will be over 15. So there are seven greens. 7 over 15. Probability of getting red when the first was green. On the second stage, the urn has 14 balls, the total of 14. And we draw a red one from 3 red, so 3 over 15. Then the probability of blue, there are 5 blue balls, and the total is now 1 less, so it was 14, now it is 13. And we can simplify this fraction. We have 7 times 3 times 5 in the numerator, 15 times 14 times 13 in the denominator. 3 times 15 is the same. 3 times 5 is the same as 15. We can cancel out 7 and 14. We divide by 7, so 14 will be 2. From 14, 2 is left. So we have 1 divided by 2 times 13, or 1 over 26. This is the probability of getting green, red, blue in this order. Probability trees. So we can represent an experiment that happens in stages using branches of probability tree. Consider the experiment that we have a bag with 10 balls, 4 white and 6 black, altogether 10 balls. On the first stage, we draw the one ball. We can get either black or white. Then on the second stage, we also draw a ball, black or white. Altogether, we have 4 different outcomes: black and black, black and white, white and black, white and white. We can draw the probabilities on every branch of this probability tree, and then we find the probability of every outcome by multiplying the probabilities along the tree, along the branch of the tree. So when we start with drawing one ball from the back, we have the probability 6 over 10 to get a black one. So there are 6 black balls from 10 total. 6 over 10, we can reduce this fraction dividing by 2, numerator and denominator will be 3. It will be 3 over 5. The probability of getting a white ball will be equal to 4 over 10. There are 4 white balls from the total of 10. And we can simplify the fraction dividing by 2, numerator and denominator, 2 over 5. On the second stage, here we have the bag of, so we have taken one black. So now we have 4 white and 5 blacks. And here we have 3 white and 6 black. So now the total is 9. The total is 9. So the probability to get the second black, there are 5 from 9, will be 5 over 9. The probability of getting the second white will be 4 over 9. 4 outcomes in favor of the event getting white from the 9 total. On the second branch, we have the bag with 3 white and 6 black. Probability of getting a black ball will be 6/9. The total is 9. Or we can use this fraction dividing by 3. Numerator and denominator will be 2/3. Probability of getting a white ball will be 3/9. There are 3 white balls from 9, and we can also simplify it to 1/3. Now we can find the probability of every from these 4 outcomes. Probability of getting black and black can be found as a product along this branch. So 3/5 times 5/9. 3/5 times 5/9. We can simplify, cancel out 5 in the numerator and 5 in the denominator will be 3/9, and we can divide by 3 numerator and denominator 1/3. 1/3 is the probability of getting black and black. Probability along the second branch of getting black then white will be 3/5 times 4/9. We can divide by 3 numerator and denominator and get 4/15. 3 times 5 is 15. Probability along the third branch will be found as a product 2/5 times 2/3. 2/5 times 2/3. We have 4 in the numerator and 15 in the denominator. 4/15. Probability of getting white and white. We multiply the probabilities along this branch. So 2/5 times 1/3 will be 2 divided by 15. So the probability of getting 2 black balls is 1/3. The probability of getting 2 white balls from such a bag will be 2/15. And we can check the answer adding all the probabilities for all 4 outcomes. 1/3 plus 4/15 plus 4/15 plus 2/15 will be 15/15 or 1, and the probability of sample space of all possible outcomes is 1. So it must be. Another example of applying probability 3. Assume that you are working in a company that has a mandatory drug testing policy. 2% of employees use a certain drug. There, we show it on this diagram. So 2% in decimal form is 0.02. Take a drug. So this is event D. Another 98% event D prime or complement of the event D do not take the drug. And then the company is given a test that is 99% accurate. So we test employees taking a drug, and with 90% accuracy, we get them tested positive for taking this drug, and with 1%, we get them tested negative. So the probability that the person is taking the drug and is tested positive will be found as a product 0.02 times 0.99. The probability that the person is taking a drug and tested negative, we multiply probability along this branch and we get 0.0002. So probability of, we want to know the probability of that the person is not taking a drug given that it is tested positive. So the given event is shown here with red, tested positive. It can be that the person is taking the drug, this branch of the tree, or the person is not taking the drug, the third branch of the tree. So the probability, this is the given event or the sample space in this new event that we consider the given event. So we will, to find the probability, we will divide by the probability of this event, the event T tested positive. The numerator of the fraction will be the probability of the intersection of not taking a drug and tested positive. The probability that if an employee is identified by the test as a drug user, the person is in fact not drug user, will be found by the fraction, the probability of the intersection divided by the probability of tested positive. And it is actually almost 1/3 of the employees of this tested positive. 1/3 of this tested positive will actually do not take drug. False positive part is because actually the percentage of these employees who do not take a drug is very big. We can determine whether the events are dependent or not dependent using the probability conditional probability. The events E and F are called independent if the probability of F given E is the same as the probability F by itself. If they are different, so the probability of the event F can be influenced by the event E, the occurrence of event E changes the probability, then they are dependent events. For example, if you draw 2 cards and the first card is not returned to the deck, then the probability of getting the second card, second card will be different. It depends on the first event. The probability of drawing the first king is 4/52. The probability getting the second king is 3/52 because there are only 3 left and there are only 51 cards left. If you consider similar situation, but we return the card to the deck, then the probability of the second king will be the same as the first king. It doesn't depend on it doesn't matter what card was the first. The probability of the second king will be still the same, 4/52. So these two events, drawing a card with replacement, are independent. Assume that we're all red in the green die. The event F, F5 shows on the red die, and the event G, the total showing on the dice, is greater than 10. We want to decide whether the events are dependent or not dependent. To determine this, we can calculate the probability of the event G itself, P of G, or the probability of the event G given F. So G is total showing is greater than 10. We have actually 3 outcomes in the event G, 5 and 6, 6 and 5, and 6 and 6. Then the total is 11 or 12 greater than 10. The probability will be 3 divided by number of outcomes in the sample space by 36, or simplified 1/12. And the event G given F, F is the first die shows 5. We take the line 5 from the table of rolling 2 dice. We take the line 5. Given the first die showing 5, we have actually only one event in the intersection, 5 and 6. So the number of outcomes in the intersection is 1. And to find the probability of G given F, we must divide by the sample space. In this situation is F, divided by probability of F, which is 6 divided by 36. So 1 over 36 divided by 6 over 36, we multiply by 36, numerate and denominate, and get 1 over 6. So the probability without F, so probability P of G is 1 over 12. The probability with F of G given F is 1 over 6. They are different. It means that these two events, G and F, are dependent events. Okay, thank you. That's all for 13.3.